So as we look at problem 2.26 on page 74, this is a really good inclined plane problem that brings up a lot of questions. Before you get into solving the problem, the first thing you need to recognize is that when something rests on an inclined plane, the weight, mg, the red arrow here, it acts towards the center of the earth. It acts vertically. And that's always true. Weight always acts towards the center of the earth or vertically. The two blue arrows, the dashed lines, those aren't actual forces separate from the weight. What they are is just looking at the weight and breaking it down into its vector components. How much of that force of weight is acting parallel to the incline, which is pulling it down the incline, and how much of it is acting perpendicular to the incline. And you have to really get a grasp on that. As the incline gets steeper, this parallel component here will get larger, and the perpendicular component will get smaller. There's the perpendicular component. It will get smaller as the incline increases. The other thing to remember about this is the angle here between the perpendicular component and the weight is going to equal the angle of the incline. So those two will be equal. So part A of this question basically asks you to find the coefficient of static friction between the block and the plane, and the block doesn't slide until the incline is made steeper and steeper and steeper, and it slides at 38 degrees. So what has happened is at 38 degrees, well, as the incline gets steeper, this parallel force has gotten larger, and friction, static friction, also gets larger to offset it. But remember, there's going to be some maximum value of static friction that it can't get any larger. And so at 38 degrees is when friction was finally overcome and the block begins to slip. So basically at 38 degrees, what you find out is that the parallel component of the weight has just gotten bigger than friction. Okay? So that's really all you do. And the parallel component is just mg sine theta from our triangle there, and that's going to equal mu times the force normal, or the reactionary force, and that reactionary force is equal to this perpendicular component, which is mg cos theta. And then solve for mu. There you go. That's problem A. So here's the situation for part B of 2.26. The block's still on the incline. The incline is increased to 49 degrees, I believe. And the question asks, how hard do you have to push up the incline so that it accelerates at 1.2 meters per second squared? First thing you should really think about is Newton's first law, or Newton's not first law, second law, of course, F equals ma. And when we do F equals ma, we can figure out the net force required. So when you do that calculation, you end up with a force of 3 newtons. But remember, with F equals ma, we're talking about the net force. So essentially what we've just discovered is that you'll have to push up the incline with a force that is 3 newtons greater than all of the forces pulling it down the incline. So we're wanting to push up here. It has to be 3 newtons more than everything else. And the things that are acting down the incline will be the parallel component of the weight right there, as well as friction. So you find the force of friction by using the equation force of friction equals the coefficient of friction times the reaction force. They give you the coefficient of friction. This component of the weight is the reaction force. Cool, so you can figure that one out. Then if you add to that, the parallel component of the weight that's acting down the incline, well, if you pushed equal to those two, it would either be stationary or moving with a constant velocity. However, if you push 3 newtons more than that, then you'll get the acceleration we're looking for. Let's try it out, see what you get, check your answer, compare it to what they got in the book, and let me know if you have any problems.